the same distance r away from the center, I have the same magnitude of electric field, and it's all pointing away. This is a case in which using Coulomb's constant is not as convenient, so I'm going to put in the permittivity form of it. So that's equal to 1 over 4 pi epsilon sub naught q over r squared r hat. So that right there is Coulomb's constant, just in terms of a different variable. And I'm pretty sure I did mention this one last time. This is the permittivity, because I discussed the permittivity is the epsilon permittivity, and because there's a subscript 0 there of free space. Times 10 to the 12. Yes, I get it. Now, if I think about, at this point, distance r from the center, I have a virtual sphere. Virtual means it's not really there. I'm just pretending I've got some surface at that distance, sort of encapsulating this charge right here. Then I know my electric field is perpendicular to that surface, that it's concentric with that charge there. And if I did the electric field times the area, that's a dot product. Well, I know that my area vector is perpendicular to the surface. Pretty sure we. 150, did we do that in 151?
Dot products?
Pardon?
Dot products?
Yeah, dot products I know we did. Do we do area vectors?
Doesn't ring a bell.
All right, so let's talk about area vectors. I spoiled some of it, sorry about that. I have an 8.5 by 11 piece of paper. Area vector, I want a vector that is going to describe that area. Well, I can just multiply 8.5 by 11 and get square inches, and I can get it in actual physical terms of area, but there is a difference between the area like this and the area like that. The area is the same of the piece of paper, the magnitude of the area is the same, but the orientation of the paper like this is different from this, and I need to somehow differentiate that from that. So I have to prescribe, subscribe. I have to give a direction to the paper. And how would you do that? How would you describe that direction versus that direction?
I had J hat. I had J hat.
Okay, so how would, keep going. You want to make I, J, K?
Yeah.
Okay, so how would you describe that one? You're fading there. Or my hearing's going pretty good. All right, he got us that far. Someone else want to pick up where he left off? How would you describe that direction versus that direction?
Would it just be the area with whatever that? Would it just be the area K hat like that? And if you tilted it back, just the same area but I hat.
So why is that the I hat?
Because I said so.
So you want to make I hat?
Sure. Sure. We'll change
Let's see if we can come up with something a little bit more uniform. I mean, that possibly
J hat.
is I hat, that's
J hat.
possibly J hat, but I need a rule there.
Yeah.
Not just because you said so. There's a deeper level there.
Whatever way the big surface is facing.
Whichever way the what?
The big surface.
The big surface is facing. So in this case, which will point in the direction of the area vector. that way?
Yeah.
And that's pretty much what they did. So if that's I, J, and K, that area is in the K-hat direction. That is in the J-hat direction. That's in the I-hat direction. The area vector is perpendicular to the surface. Now, if I've got a two-dimensional surface, if I have a two-dimensional surface, is my area vector pointing side view, jaunty tilt view. If I have a two-dimensional surface, is that the direction of the area vector, or is that the direction of the area vector?
They both are.
I'm gonna nitpick that. Yeah. It's not both.
It can be either.
It's either. So if I have a two-dimensional surface, my area vector could point in one of two directions. If it's a three-dimensional surface, the convention is, the powers that be said, it is always towards the outside. So so that is my area vector, or that is my area vector. It's one or the other, again, not both. If I have a three-dimensional surface, the area vector is pointing outwards. However, I assume in your own notes, you will draw three-dimensional much better than that. So let's talk about the dot product. Questions before we talk about the dot product? I assume most of you have fond memories of the dot product. Now I know there have been, when did you take 151?
I think so, the stuff you keep repeating from physics 1, I did not take that.
You did not take physics 151?
No, the material we took was different.
Okay. All right. So one of you will demonstrate that you understood dot products so well that you will understand. And you will impress me that you remembered. Although it's been longer for some of you than others. Someone want to describe what a dot product is?
The multiplication of vectors.
All right. There are two ways of multiplying vectors. There's dot products and,
Cross product.
okay. What's the difference between a dot product and a cross product?
Cross product vectors don't go the same way. And dot product does.
Okay. I'll go with the spirit of that.
I don't really remember if this is right, but isn't dot product, you essentially, like, I don't wanna say combine, but like you combine the vectors, whereas cross product, you get them like separately.
I think I know where that's coming from. I'm gonna say no, but I think when it's all revealed, you're gonna go, yeah, that's what I meant.
Well, I know that for dot product, we were dealing with like a X and Y axis essentially, like there's the horizontal or vertical, whichever way you orient it, and then for cross product, we were dealing with horizontal, vertical, and then also like in or out.
Okay. So bits and pieces are being remembered, Luis?
Is dot product parallel vectors and cross product perpendicular vectors?
There we go. That's
There we go.
when you multiply vectors with a dot product, you're multiplying the parallel components. So if I have a vector like this times a vector like that, so this is A and B. What I would do is I would figure out how much of A is in the direction of B, or how much of B is in the direction of A. I would break A up into its components. So this would be the part of A that is parallel to B, and I'd multiply that length times that length. Dot product is also known as a scalar product.
It's all coming back now.
Scalar product because the answer is a scalar. There's no direction in the answer of a dot product. Cross products, which we will get to again later, just to bring back the warm fuzzies. Cross products, it's called a cross product because the symbol you use is the cross. So cross product, we use the cross, dot product uses the dot. Dot products are scalar products, cross products are vector products. So this will have a direction if I do a cross product, A cross B. I multiply the perpendicular parts, so I would multiply this length right here and the perpendicular part to get the cross product. And then the direction, right hand rule, don't worry, we'll do plenty of right hand rules later on. Put the hand in the direction of the first vector. Curl your fingers the shortest way to the second vector. Your thumb points in the direction of the cross product. So the cross product of A cross B would be into 4.
Nightmares.
Now,
Nightmares, the right hand rule.
a dream, that's what I heard.
Nightmares.
When we get into magnetism, that's when we will face cross products again. So, for right now, dot products, you multiply, you've got two vectors, you multiply parts that are parallel to each other. There's no direction in the end. So, if I look at the electric field on my surface, my pretend virtual surface here. Now, of course, we have a special name for it. Instead of just pretend or virtual, it is known as a Gaussian surface, more specifically, a Gaussian sphere. So this make-believe surface here is known as a Gaussian surface. Okay. So my area vector, because it is a sphere, it's a three-dimensional object, the vector points outwards. The area vector points outwards. My electric field also points in the same direction, and so my multiplying the electric field times the area vector, at any point is just multiplying the magnitude. So multiplying the magnitude of the area times the magnitude of the electric field, and I end up with whatever my electric field is times the area of that sphere. In this case. So we write in this case. So what I end up with there is if I do E dot A, my electric field is 1/4 pi epsilon sub naught Q over R squared times the area of that sphere, surface area. So if I have a sphere of radius little r, what's the surface area? What is the surface area of a sphere?
2 pi r.
That
Wait,
circumference of a
that's
circle.
Pi radius squared. Pi radius squared.
That's the area of a circle. Do you know the volume of a sphere?
Isn't it like 3/4 something?
4/3 something.
Oh.
All right,
That's the volume? And that was the volume?
volume. All right, so volume, let's start out with area of a circle, pi r squared. circumference of a circle, 2 pi r. Who in here has had some calculus? Take the derivative with respect to r.
Oh, yeah.
The volume of a sphere, 4/3 pi r cubed. The surface area of a sphere, take the derivative with respect to r.
So pi r squared.
Yep. Now, if you have no idea what I mean by take the derivative with respect to r, don't worry about it, beyond the scope of the class, that's just a quick aside. So the area of a sphere is 4 pi r squared. The 4 pi's cancel out. Wait a second, the r squared cancels out. So if I am looking at some point outside of that, I know that this electric field times the area is just equal to the charge that's enclosed divided by epsilon sub naught. Seems rather nice that it's simplified down to that. Now this electric field times the area vector, you can't just let that go without calling it something else. This is known as the electric flux. Symbol for electric flux. Capital Phi, subscript E. To differentiate it from the magnetic flux, because that of course exists too. Yes?
Are you nitpicky about how we choose to write phi, capital phi? Does it have to have, can it be sans without?
How do you differentiate it from the lowercase one? Let's make it bigger.
Yeah.
I will say from context, I probably can figure it out. However, if
You would prefer it with this card.
I prefer it with the serifs, unless you've got some other way to differentiate it from the lowercase. We have enough letters where upper and lowercase look the same except for size, like C. And when I make my P's. But when you're going through elementary school, how do they teach you to write your capital Greek letters in cursive? I'm just trying to think of how many, my mind would have been blown at a certain age, learning cursive. All right, you have all your letters, now let's try the Greek letters. I think Mom would have appreciated it. Okay. So what we've now broken it down to is that the electric flux through the sphere is equal to whatever the enclosed charge is over this constant, epsilon sub naught. And we will now take it one step further. In general, the electric flux through any closed surface is going to be equal to the charge that is enclosed inside the surface, closed within surface, divided by this constant. This has a name. This is Gauss's, or Gauss, Inspanier, Gauss or Gauss's law of electricity. This is some part of my handwriting you can read there. Are you going to handwrite shame me?
Of course not, Dr. Fox. Can you refresh the closed surface, open surface?
All right,
I get it, but
a closed surface, there's an inside and an outside. I cannot get from one point to the other without passing through the surface. That would be a closed surface. So this would be a closed surface, because if I'm inside and want to get to the outside, I can't get there. If this was, say, a two-dimensional sheet, it's not a closed surface because I can get from here to here just by going around it. So open surface, closed surface.
okay.
There are a set of 4 equations that are now referred to as Maxwell's equations. I will let you know, Maxwell did not call them that. He actually, strangely for a physicist, was somewhat humble. Gauss's law of electricity is the first of Maxwell's equations. For those who have had calculus, this is just a 15-second aside. This also can be written as the integral of E dot dA Q closed. That's the calculus, the integral form of the exact same thing. I also want to point out, we've had only one physics equation so far in this course, Coulomb's law. All the rest of it are math and definitions. So this is Coulomb's law disguised, but it's in there. All right. Questions? Then let's apply this concept. I have a sphere, a conducting sphere. Solid. I throw excess charges into it. We've already discussed the charges will move to the outside. I'm now going to create a Gaussian sphere inside of this charged sphere. I'm going to be inside. I can't treat this as a point charge in the middle because